The general idea that most people have about the universe began to take shape in the 17th century by Isaac Newton when he imagined that the universe is a huge machine operating according to a precise and stable system. And if we could understand the laws that govern it, then we could predict everything that will happen in the future simply by knowing what happened in the past and what is happening now. Indeed, Newton established laws that explain everything from the movement of objects, gravity, but later, scientists like Einstein, Niels Bohr, Max Planck, and Schrödinger came along and changed the table, saying that this universe has no catalog and that the things we see as real are in reality not as we imagine them, and that time itself is not a straight line with a past, present, and future. Rather, the past can be affected by the present, and the future can also change what happened in the past. Peace be upon you, since Thomas Edison invented the light bulb in 1879, and assuming he was the real inventor, all of Europe was at the peak of joy. Finally light entered their homes. However, they did not know that this was the beginning of confusion, not the end. Many questions were hidden in the darkness and appeared as soon as the world was initially lit up. Edison's light bulb worked by a wire with an electric current running through it. This current made the wire heat up, and when it heated up, it glowed. This was a great leap at the time, but scientists started asking questions instead of celebrating. Why does it glow when the wire heats up? Why does the color of the light change when the temperature increases? First, it turns red, then yellow, then white. Why does it turn white, and then stop? Why does it never turn white again? 3 questions that no one knew the answers to, and every attempt to answer them led to a Nobel Prize. Scientists understood that the solution would not come until we knew what the material itself was made of. At that time, it was believed that matter was made up of small, solid balls called atoms, or particles similar to billiard balls, that were indivisible and had no charge. But in 1897, a scientist named Thomson discovered that inside the atom were smaller things with a negative charge. He called them electrons, and since the entire atom is electrically neutral, it must have a positive charge to balance the electrons. He said that the atom is like a watermelon. The black core is the electrons and the rest of the watermelon has a positive charge. They told him, "Great, you deserve the Nobel Prize." But after 10 years, Rutherford said, "No, this doesn't make sense." He performed an experiment with alpha rays on a gold slide. If the entire atom was positive like a watermelon, these rays would have bounced back, but he found that most of the rays passed through and only a small part was reflected. He told them, "Then the atom is not a watermelon. Listen to me. The words that are like gold are that the atom is basically empty space, and the positive nucleus is very small in the middle, and the electrons revolve around it like the solar system." And he won the Nobel Prize. After that, their uncle Max Planck came and said, "I am not going to talk about matter. I am going to talk about energy. Energy is also made up of small units that I called quanta." They told him, "That means energy became pieces like atoms." He told them, "Yes, and you will believe me in the end." He called it quantum physics or quantum mechanics. It was a crazy idea at the time, but Niels Bohr heard what he said and said, "That's it." He began to explain the subject of light with it. The one who comes out of the wire in Edison's light bulb said that when the electron takes energy, it jumps to a higher orbit and after a while it returns to its place and emits this energy in the form of light. That is, if you heat the wire slightly, the electron takes a small amount of energy and jumps to an orbit above it a little bit, and when it returns, it gives me weak light. Red heats up more and gives me stronger light. Yellow heats up more and gives me white light. But if you give it too much energy, the electron will not be able to go to another place because it needs a certain number of quanta, so no new light is emitted. This answered the 3 questions. They helped me with the science and Max Planck's Nobel Prize, but the explanation was a bit terrifying because the electron does not move between the orbits. It disappears from one orbit and appears in the other. God knows how. At that time, Einstein was working on the photoelectric theory and noticed something strange. When the electron falls on a wire, it can generate an electric current, meaning it can liberate the electrons. But the surprise is that the intensity of the light, it is not the light that moves the electrons, but the color of the light that makes the difference. That is, a light blue light can move the electrons, but a red light, strong, it may not do anything, and this means that light itself is composed of energy quanta, photons, and each color has a different energy, and the electron takes the whole that suits it, and the result is that Einstein won the Nobel Prize for this theory. But here the crisis began, because the electron is a particle, something with mass, so if light can move it, then it must also have mass or a body, and this brings us back to Newton's old idea that light is a particle, but other scientists after Newton proved through experiments that light is a wave, not a body, and a wave means a disturbance that occurs in a medium, like a water wave. A wave does not mean the water itself, but rather disturbances that occur on the surface of the water. So how can light, which originally has no mass, be just a disturbance? There was great confusion, and Einstein said, "Guys, light is neither a wave nor a particle, it is both." This was the first dangerous sentence in quantum physics. At that time, a student named De Broglie said, "If light is a particle and a wave, then the electron can also be like that, and if the electron is a wave, then the whole atom is a wave and matter itself is a wave. We as humans are waves." He won the Nobel Prize, but the question he left behind was, if the electron is a wave, where is it inside the wave? Schrödinger came and created the wave equation that explains the movement of the electron. Where is its location? I don't know. How do we understand this? We don't know, but he won the Nobel Prize. Heisenberg came after him and said that it is not possible to determine the location and speed of the electron at the same time. You either know how it is moving or you know where it is, but both together are impossible. He established the uncertainty principle and won the Nobel Prize. Then Max Bornau came and said that we can calculate the probability of the electron being in a specific place. I mean, not where it is, but it could be here at a certain percentage or here at a lesser percentage. He developed the Schrödinger equation and won the Nobel Prize as well. And the conclusion from my point of view. From De Broglie's point of view, you are a mentor, and from Born's point of view, you are a possibility. If this sounds strange, let me tell you that the mobile phone in your hand works. With this physics, the LED, magnetic resonance, and electron microscope are all products of quantum mechanics, and what is coming is much stranger than what has passed. Don't forget to like, comment, share, and subscribe to the channel, and activate the bell button, because I promise the next parts will be much stranger than this one.